Okay, hi everybody, this is Dr. B, and let's give you some assistance with the molar conversion practice quiz. The actual quiz you will take in a couple days will be identical with just numbers changed. So why don't we give this a shot? This is the summer assignment practice quiz for Dr. B's AP Chemistry class, and let's get going. Let's answer the first question. It says, what is the mole? Well, it's just a number, so I'll write a number. What is that number? 6 times 10 to the 23. I'm going to write 6e 23, because that's what it is, where e would mean times 10 to a power, and that's how many is a mole. And what is molar mass? Well, as the name implies, it is the mass of a mole of anything. So if you had, I don't know, pencils, it would be the mass of 6 times 10 to the 23rd pencils. And that would be a lot, by the way. So let's apply both those terms. A mole of water, that's H2O, has a mass of 18 grams because hydrogen checks in at 1 gram per mole, and oxygen 16, so 1 plus 16 plus 1, that's H2O, equals 18 grams. We're rounding a little bit, but if you had 18 grams of water, you'd have 6 times 10 to the 23rd molecules of water. So let's put 6e23, and there you go. Now let's create a mole chart for burning 32 grams of ethane, C2H6. It's balanced for you. Notice that it's 2 to 7 to 4 to 6. That's a little unusual, but convince yourself it's true. For example, we have 4 carbons on the reactant side. See that? 2 times 2 carbons. And we have 4 carbons on the product side. Check all of them and you'll see that it's balanced. And by the way, we'll be using masses like hydrogen checks in at 1 gram per mole. Oxygen checks in at 16 grams per mole. You can find these on any periodic table. It simply means that oxygen is 16 times heavier per atom than hydrogen. And carbon checks in at 12 grams per mole. We'll be using those numbers right away because for starters, let's put in molecular weights. Now that's just the molecular weight per molecule. It doesn't matter what the prefix is. Those will apply later. Since it's C2H6, each carbon is 2, that's 24, plus each hydrogen is 1, 24 plus 6 is 30. And I do notice that we have 30 grams. Well, 30 grams is a mole, 30 grams per mole, so we have 1 mole. And anytime you have a mole, you have 6e23, 6 times 10 to the 23rd molecules. Fine. Now let's finish our molecular weights. 2 O's checks in at 32 grams per mole. Carbon is 12, and each oxygen is 16, so 12 plus 32, it checks in at 44 grams per mole. And water, as we pointed out before, checks in at 18 grams per mole. Fine, those numbers will be handy because we do have 1 mole here, do we not? But we see that every 2 requires 7. That would mean every 1 molecule would require 3.5. So we do have 1 mole, which is just a multiple of molecules, is it not? So we have 3.5 moles is what we're going to need there. Well, if a mole checks in at 32 grams and we need 3.5, 32, 64, 96, plus a half, that's 16, 106, I get 112, I hope that's right. Notice that we're starting with 144 grams of reactant. The law of conservation of mass and hopefully some common sense tells you we better end up with 144 grams of product. So let's see if it will equal it. Okay, 2 of these will make 4 of those. Do you see that? Therefore, 1 of these will make 2 of those. So we're using these ratios throughout. This 2 to 7 to 4 to 6 should be the same as 1 to 3.5 to 2 to 3. 2 moles is 88 grams, right? Since 44 grams is a mole, we have 2 moles, so that's 88 grams. And here we have 54 grams. I do notice that 8 plus 4 equals 12. It's going to end in a 2. 88 plus 54 does equal 142. It checks. When you do that, you know you got everything right. 3.5 moles. Well, 1 mole is 6 times 10 to the 23, so we've got 18 plus another half, I think 21 E23. That's ugly. You could say 2.1 E24, or the best way is 2.1 times 10 to the 24, but I'd accept any one of those. 2 moles would be 12 times 10 to the 23, which of course is 1.2 times 10 to the 24th, but I won't bother writing it. This would be proper, and in fact, you can enter it into a scientific calculator that way, so I think that's fine. And here we have 18 times 10 to the 23rd, because 1 mole is 6 times 10 to the 23rd, and we have 3 of them. So we have 18 times 10 to the 23rd, and that's page 1. Let's continue. Limiting reactants. It says we're reacting 7 grams of N2 and 7 grams of H2. Well, that's ridiculous because I can tell that 28 grams requires 6 grams. Can you see that? And, oh, by the way, HONC. Hydrogen, we said, is 1 gram per mole. You can find that on any periodic table. Oxygen, 16. Nitrogen checks in at 14. That's where I got that 28 from. And carbon is 12. We're reacting 7 and 7. So if we had 7 grams of hydrogen, we would need over 4 times as much nitrogen. So I can already tell we don't have enough nitrogen. But let's go ahead and do it. I'm going to do it the quick way. And then I'll go ahead and show you the long way. It'll take a bit of time, but we'll go ahead and do it. The quick way is 7 grams equals 0.25 moles. I did that in my head because 28 grams is a mole, right? 2 times 14, and I have 7. That's a fourth of 28, so I have a quarter of a mole. It will make how much ammonia? That's the question, right? Amount of product. Ammonia is the product. These are the reactants. This is the product. So if I got a quarter mole here, 1 makes 2, it'll make 0.5 moles of NH3, right? Because that's what we're making. And each NH3 checks in at 17 grams per mole, 14 plus 3. And so we need a half of that. Half of 17 is 8.5, and I'm going to write equals 8.5 grams of NH3. That's the fast way to do it. And if you want to do it that way, you could go ahead and skip this little calculation. But if you want to do it, these are 3-step gram to gram conversions. What do we start with? We always start with what we're given, which is 7 grams of N2 and 28 grams of N2 is a mole of N2. And notice grams cancels nicely. That's how I see I have a quarter of a mole. But anytime I react a mole of N2, it will make 2 moles of NH3. How do I know that? One of these makes 2 of those. And those 2 moles of NH3, each mole of NH3 checks in at 17 grams. That's where I said I have a half a mole, and a half of 17 is 8.5. And notice the moles and the moles of the other stuff cancel nicely, and we end up with 7 times 2 is 14 times 7 divided by 28. Plug that in. I'm not going to bother. I'm pretty sure it's 8.5 grams of NH3. Now, if we have 7 grams of H2, I think we can make a lot more product because each atom is only 1 gram per mole. Each element, I should say. And so we have 7 grams. Let's do it the fast way. Or the quick way. We have 7 grams of H2. This is 2 grams per mole, is it not? So we have 3.5 moles. And that's this stuff. Ooh, it'll only make 2/3 as much, right? 3 makes 2, so I'm going to do 2/3. 2/3 of 3.5, so I'm going to actually enter that in. 3.5 times 0.6667. That should give us more than enough precision. And we have 2.33 moles of ammonia, all right? And now that's 2.33 times 17. So now we'll just do times 17. And that's 39.6 grams. That's a lot. Equals 39.67 grams. If you want to be picky, we have 2 sig figs here. So I'm going to round this to 2 sig figs. And I'm going to say 40 with a decimal place grams of NH3. Let's bravely put it here and see if we get the same answer by doing it the slow way. Well, what do? We start with what we're given, which is 7 grams of H2. And I know that 2 grams of H2, and you could do it more precisely if you wanted to, using more precise numbers, but I think we're okay. It probably is about 2.0 grams of H2 is a mole of H2. That's how I figured out I have 3.5 moles. But every mole of H2, and there's the number in front, 3 moles will only make 2 moles of NH3. That's 2/3. That's why I did 2/3 of that to get the 2.33 moles. And then every mole of NH3, notice anything that goes on the top left, we put on the bottom right, so the units will cancel. A mole of NH3 checks in at 17 grams of NH3, just like it did before. And let's actually check it, because I'm a little nervous. Let's clear this out. And we'll do 7 times 2 times 17, that's the top. 7 times 2 times 17, enter, is 238. And we're dividing that by 6, right? Let's divide that by 6. Divided by 6, enter, and that's the same number, 39.67, rounds to 40. Life is good. We'll circle it. Notice it has the number, the units, and whatever it is, in this case, ammonia. Okay, let's continue. The reaction can only produce up to, the lower number wins always, 8.5 grams of ammonia. Why? Well, you're out of nitrogen at that time. Out of N2 at that point. All right, you can't react nitrogen with hydrogen if you're out of nitrogen. Fine. This type of problem can also be solved more rapidly using molar amounts. We did, and we showed it the quick way. So 1 mole of N2 is 28 grams. Reacts with 3 moles of H2, that's 3 times 2, which is 6 grams. Since we have 10 grams each, the limiting reactant must be N2 because we have 10 grams of, let me make sure I get this right, 10 grams of N2. 10 grams, 28 needs 6. So 10 grams of H2 would need, right? 6 needs 28, would need greater than 40 grams of N2. Only have 10. Get it? We don't have enough. We would need 4 times as much nitrogen as hydrogen, but we certainly don't have it. So that works for me. This reaction shows that only calculation number, I don't know. Oh, I see. It must be this one. Calculation number 8, I guess, is needed to solve this problem because this shows that you don't need to bother with the bigger number. It also shows you can just do it the quick way. I encourage you to do it either way. And then your final answer is this reaction can produce up to, because life is not always perfect, 8.5 grams of NH3. We circle that. There it is, and we're done with that section. And it's time for our last page. Let's determine the percent composition of methane. You might recall that carbon checks in at 12 grams per mole. Then each hydrogen checks in at 1 gram per mole. So it's H4. I'm going to write 4 grams per mole. So a mole is CH4 is 16 grams per mole. And can you see that 12 of them came from the carbons? So that's 12 out of 16. I'm going to write carbon is 12 sixteenths. CH4 is 12 sixteenths carbon. That's 75%, right? 12 divided by 16 times 100%. That's how you do it. Take a mole and see, divide up the pie. See what it mostly comes from. The 4 sixteenths is a quarter, is it not? I'm going to write 25% carbon, 75% carbon, 25% hydrogen. And that's our answer, and it checks out. A mysterious substance has the following data. It's 5.88% hydrogen. See, you're getting the percent composition. Now you got to go back the other way and find its formula. And it's 94.12% oxygen. That does add up to 100%. What's the empirical formula? That's the simplest ratio. Well, I could see that this is H is 1 gram per mole. So if we had a 100-gram sample, H is 1 gram per mole. And if we have 5.88 grams, that would be H 5.88, right? Because you have 5.88 moles, right? 1 gram per mole, and you have 5.88 grams. And oxygen checks in at 16 grams per mole. So every 16 grams is a mole. We have 94 grams. It sounds like, oh, I don't know, 6 or so moles of that. Let's call it 94.12 divided by divided by erasable pen, 16 grams per mole. And now we better punch that in because 94.12 divided by 16 equals 5.8. Well, that's a familiar number. So it is H 5.88, O 5.88. I can tell that's H1O1. I always use the mantra divide by the little guy. Well, they're both the little guy. So we have 1 hydrogen atom for every oxygen atom, H1O1. That's called the empirical formula. We will circle that. Now, it could be any ratio of that. It could be H6O6, things like that. And to find out what the actual formula is, we call that the molecular formula. That's the real thing. Based on the fact that it's 34 grams per mole, we're going to scale. H1O1 equals 17 grams per mole, right? 1 hydrogen, one oxygen. That's 1 plus 16 is 17 grams per mole. So we must have twice as that, much as that. Molecular formula equals H2O2, right? Just double it. Notice that the ratio is still 1 to 1. We just have scaled up, and now we have 2 plus 32 equals 34, so I am sure that's right. Blah, 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 blah. By the way, knowing that hydrogen, and I'm just kind of going a little off topic here. Hydrogen always forms, in terms of bonds, always forms 1 bond, oxygen 2, nitrogen 3, carbon 4. Notice each hydrogen does have 1 bond. Notice each oxygen does have 2 bonds. And so this is called hydrogen peroxide, and that's the only molecule that would fit this formula while obeying what we call the honk rules. And that is a guide to the practice summer assignment quiz you're going to get in a couple days for AP Chemistry. Like I said, I'll just change the numbers, right? I'll just change that. I'll just change it from methane to something else, and I'll change the combustion reaction before, that sort of thing. So see me if you have any questions, and good luck on your practice quiz.